Welcome everybody. In this video, in this series on condensed matter theory, I want to talk about n-particle states. And it's going to be a relatively brief video where we just give an overview of the notation and the Hilbert spaces that we generate first for one-particle states, and then how we generate n-particle basis functions from that, and how from these n-particle basis functions we can generate n-particle states. So when we work in quantum mechanics, we can write our wave functions as a sum over orthonormal basis functions, and for one-particle states we can define a one-particle basis. So these are wave functions that can occupy a single electron, and we can make a basis which we label by tau, going from 1 to n. In atomic physics, these would be the atomic orbitals or your hydrogen orbitals, where tau then labels both the principal quantum number n, the angular momentum L, and the projection of the angular momentum on the z-axis m, and then you have spin, also the spin projection on the z-axis sigma. So we just put that in a single variable, tau. For plane waves, this would be the momentum of the plane wave k. It can be anything you like. Then we have our wave functions, psi of tau as a function of r, or we can say we create particles with quantum number tau out of the vacuum, which is equal to the ket of psi of tau. So that's for a single electron or a single particle. When we have n of such particles, then we can define an n-particle basis. And for that we can choose capital N single particle basis functions and occupy them with electrons. And we do this, of course, fulfilling Pauli principle, but writing things in second quantization that is immediately fulfilled. So we can define a subset out of all possible orbitals of n particles. So we do not take all small n, but we only take capital N, or a subset of n one-particle basis functions. From the small and possible basis functions that we have. So we can calculate the number of possible sets that we can make, and that is given by small n over capital N, or n faculty divided by n faculty times n minus n faculty. That's the number of possible sets di. We can now generate n-particle basis functions, psi I, as a product of tau equal of element in di, a dagger tau out of the vacuum. So for two particles, capital N is 2, I can make sets with particle 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 2 and 5, 3 and 4, 3 and 5, etc. All possible ways in which I can pick two elements out of the small n elements that I have. These different sets can then be used to generate all possible two-particle wave functions. These, however, are not the eigenstates of our system. Although in the periodic table, of course, we say, well, we build up our wave functions by filling the hydrogen orbitals. You get corrections to this, and you get mixing, and in general these are not the eigenstates. So for a general n-particle state, well, these might not be the eigenstates, but they are all possible states that we can take. They are orthonormal, and as such they form a basis for our n-particle Hilbert space. So a general wave function with n particles can be written as a sum over all possible Slater determinants with some complex prefactor and then our single Slater determinant states. And this is how we, in general, can always write down our wave functions states and states of n particles in a system. It might not be always the most efficient. Of course, making different linear combinations, unitary transformations can change a lot. We will discuss some of that later in this lecture and a lot in the next lecture, where we will really talk about general n-particle systems with entanglement interactions between our electrons. But for now, this is sufficient that we know this is always a basis to which we can project. Might not be the smartest basis, but at least this is an option. Thank you very much for your attention. And the next videos will continue with the Drude model, where we will skip everything related to quantum mechanics, but are able to describe some of the material properties that we see around us. And of course, we will find several cases where we cannot describe the material properties, because quantum mechanics is really an essential ingredient of condensed matter theory. Thank you very much for your attention. Stay healthy. We see each other later.